Thank you, everyone. Good afternoon. So I'm going to present our team's research. So we work on efficient and robust machine learning with tensor networks. So as we know that now in recent years, the AI has a big change. So we need a massive, large-scale data set, and the model size grow also dramatically. We have a large models, and also it costs a lot of massive computational resources. Especially the example is a large language model. So, but actually in many real applications, so especially like recommender system or biomedical applications, sometimes we don't have massive training data with well annotated labels. So we need to explore the data structure to find the more knowledge from the data itself without many training samples. And some typical application like recommender system or image imprinting is in particular hyperspectral image processing and graph prediction. So the question is how to find knowledge from incomplete and limited data, and the data may sometimes noisy or even corrupted by the noises. Especially the adversarial perturbation is very difficult noises. From the model perspective, so the large model have a lot of parameters, and such large parameters gives a heavy computation and slow training time and the inference time. Also, such big model makes the deep neural network becomes a black box, which is difficult to interpret, and also lack of robustness to adversary perturbations, which is a very serious problem for security. So we start from very fundamental methods like how to analyze tensor data, especially when the data has a multi-dimensional structure, which is represented as a multi-way tensor. So when the data has many missing values or noise values, how to capture the data structure and reconstruct the data. So some challenges is data efficiency. We try to develop algorithm which can use very limited observations to have a high performance recovery accuracy. Also, algorithm need to be scalable and efficient. And theoretically, we want to have exactly recovery guarantee. And basically, one task is tensor completion. So the main objective is given a partially observed tensor Y. We try to find a good approximation tensor X. And the first term is fitting error is minimized. And in general, this problem is ill-posed. We need a lot of regularizers to find optimal solutions. And the structure regularizer is our main point to work on. So one general assumption is the low rankedness, which is very powerful and useful for many cases. So we can assume data has a low rank structure. Then we use a limited number of hinges to reconstruct the whole data. But in tensor case, the low rankedness is not well defined. We need to define how to define the low rankedness of tensor as a nuclear norm. So there are many different ways. And second, we can assume the data satisfies some kind of tensor decomposition structure, which we call the tensor network. In this case, we need to also choose optimal rank and optimal tensor network structure. So this is one example. We propose a specially TSV-based nuclear norm, which is defined on the tensor data. So we show that using such nuclear norm on minimization, we can reconstruct the original data exactly. And some error bound is given. We can see that by using different definition of nuclear norm, the error bound are quite different. such as in this case, we assume the tensor has low rankness along all modes. So here is a summation of nuclear norm along different modes. And the second one is we assume tensor can be divided as 3 components, and each component satisfies one low rankness on each individual mode. So that means maybe this data only satisfy low rankness on first mode, but not low rankness on second mode and third mode. So in this case, the main component will be absorbed in this one. Then we can still find the good approximation by using such nuclear norm. At the same time, when the data is corrupted by noise or the outliers, and in general, the outlier, we can assume some assumption like sparsity to capture the noise or robust tensor decomposition. But here, we especially consider the outlier has also some kind of structure. We think that outlier may satisfy the different sparsity along different modes. So in this case, we can capture more specially designed like outliers when the outlier is such sparsity along one mode, but not all in general sparse. So this is one, I think there are some specially applications in brain signal processing. When you do the EEG recording, some channels may corrupted, but other channels are well connected. In this case, the whole channel is corrupted by outlier. And in this case, is in the channel domain, there is a sparsity outliers, but in the time domain or frequency domain, they may not have outliers. And then we can define such kind of new L2 norm to capture such case of outliers to minimize this, and we can develop like tensor low rank approximation by assuming the sparsity of outlier to capture different outlier on the different mode. Here is some theoretical result. We show how error changes. Usually it changes linearly with the square of tensor ring rank, and also some number of outliers. So maybe I will skip the result. But when the data in real world, sometimes the data usually only like a third order tensor. One approach is we try to make the tensor, make the data more high order case. So this is one typical example. Given an image, we try to tensorize data as a very high order tensor. When the tensor is very high order, we can use a more powerful method, which we call the tensor network, which is more flexible tensor decomposition extensions to high order case. Then in this case, we can capture more information from the data itself. And here is the general tensor completion optimization functions. So we assume the tensor low rank tensor Y satisfies the tensor ring structure. Then we impose the low rankness on the tensor ring core tensors instead of on the whole tensor Y. By using this, we can improve the efficiency because this optimization on the core tensor have very efficient computation, very fast algorithm. So what's tensor network? Actually, it's a very straightforward extension of tensor decomposition for third order tensor to the n order tensor. So if the tensor is n order, they are more flexible, many different tensor network structures, which are widely used in the quantum physics to represent many body wave functions. But in machine learning field, they are not very well applied. The idea is how to represent n-order tensors as a contraction of n small core tensors. And the connection between cores is some kind of multilinear operation. So here is one particular example, which is a tensor ring decomposition. Given an n-order tensor X, we can decompose X as n small tensor core tensors, and each core tensor is a third-order tensor, but the size is quite small, and all core tensors are connected. The connection means multilinear contraction operation. And how to understand this? So given one element in the tensor case, so there are n indices, and from the first indices, we can find one slice from the first core tensor G1, and we take out one matrix, and according to second index, we can get second slices from second core tensors. Then we do the sequential product of all matrix. Finally, we have a trace operation because this is a loop structure. So then there are many algorithms to decompose tensor as many like tensor cores. So, but most tensor decomposition methods, we still need many assumptions like data distributions assumptions. We assume the likelihood function will be Gaussian, or will be some kind of portion distribution when the data is integer. And also we need to assume the tensor network structure. That means we need to assume like which tensor decomposition structure you will apply it. And such assumption is very limited when we apply it to the real data, because we don't have so many prior knowledge about that. So our work is to try to how to relax these assumptions and develop a more flexible tensor decomposition method. So first step, we want to first extend the standard tensor decomposition from multilinear case to nonlinear case. So this is one standard CP decomposition. We can see that each element can be represented by the inner product of three vectors. This is a linear case, linear interaction. So, and the Tucker decomposition is also linear interaction with summation of all components with the different rank. So now we try to make this interaction from linear case to nonlinear case. So how to do this? One simple way is to using Gaussian process. We assume all the latent factors. We can compute the kernel function between latent factors. We assume they can map into the element as a Gaussian process. It's a function prior. But this is very difficult to solve because joint distributions, we have a very huge kernel function, covariance matrix. And also in this case, we still assume the distribution is Gaussian here, and it's not applicable to data or binary data. And the cubic complexity with n squared, n cubic, and n is a number of entries in the tensor. So to solve these issues, we propose a very flexible nonlinear tensor decomposition method. So instead of model the conditional distribution, we try to model the joint distribution between latent factors and data. And such joint distribution we model by using a neural network, because it's a very powerful function approximation can be used to approximate any functions. Then we assume our joint distribution is such kind of energy-based model. And in the energy-based model, the function f theta is a neural network. The input is data x and the latent factors. Then by using this, we actually can capture any kind of more flexible distributions of the data tensors. Also, we don't need to assume the tensor decomposition structure. That means we don't need to assume CP, Tucker, or tensor ring, tensor chain. And then to learn these models, also we borrow some self-supervised learning technique to use constructive learning technique to learn the latent factors from the tensor X. So here is some experiment which we can show that when the distribution is different, like beta distribution, mixture of Gaussian and other distributions, our model can capture very well with the data distribution, different distributions. So next, I will talk about how to apply such tensor method from the analyzing the data to analyze the model parameters. So one task is model compression, because neural network has a very big model. So how to make the model smaller but keep the same performance is a very challenging task. So there are several different ways, like quantization or many other, like cut some connections are typical way to make model compression. And there's also one method using low-rank tensor network to compress the model. So we assume the model parameters W can be tensorized as a high-order tensor and then represented as a tensor network. By using this, actually, we allow some kind of error, approximation error, but the number of parameters can be dramatically reduced from the Mn to the dis root of Mn. Of course, it depends on the rank. So that means if parameters has good low rank structure, we can compress a model very a lot. And later we keep the layer input multiplied with the parameters as a tensor network. We can use tensor network operations. Also, we can use such tensor operation to change the standard, like a recurrent neural network, from the standard standard form to some kind of a tensor form. So the idea is we change this layer from the one layer to input to output this function as a tensor product layer. So we can concatenate the input X and the hidden state H first. Then we do the tensor product with itself, P times. Then after that, we use a tensor G to transform the input to output. Yeah, please note here, we actually remove this nonlinear function sigma because tensor product actually is already nonlinear. So in this case, actually, the good point is we don't need to use this nonlinear activation function, but the disadvantage is because we use a tensor product, which will generate polynomial growth over data dimensions. So in order to solve this problem, we always need to decompose parameter G as also a tensor network. Then the computation efficiency can be reduced down to the linear case. But the model expressiveness can be dramatically improved. And we also prove when this P is larger, we can generate long memory. And if the P is quite small, we will have a short memory. And how to choose P, we also develop another part to learn the P from, we change the P from discrete value to continuous value. Then we can learn the P from the data. So when we apply tensor network to represent the parameters, we also occur some problem is that how to choose a rank and how to choose permutation, also how to choose tensor network topology. Of course, previously I present the flexible tensor decomposition, which relaxes this assumption for data. But for this parameter case, we still need to choose these structures. So then the next question is how to choose a tensor network structure. We call this problem is structure search. And the difficulty is it's the number of tensor network structure candidates increase growth with exponentially with the order of tensor. So it's quite difficult to solve. Also, we need to know the our objective is we try to approximate like model parameters as the tensor networks. And the first part is model complexity. We hope to use small number of parameters, but but at the same time, we hope the model expressiveness is also same powerful as the original neural network. So this is our goal to learn the tensor network structure. And next, we need to convert tensor network from the tensor network problem to a graph problem. So this is a typical tensor network, tensor ring. Then we represent this tensor ring as a graph representation, which is the adjacency matrix. And if the first tensor called G1 and G2 has connection, there's a value. If there's no connection, it's a zero. And also here R1 means the rank between the two tensor cores. So in this case, if we can learn the good adjacency matrix, we can learn the tensor network structure very well. So next, we developed several algorithms to learn this, because this is not continuous optimization problem. We use some random sampling from the neighborhood and then choose optimal samples, and then we update to a next step. Also, to improve the efficient convergency, we try to, like when we do sampling, we first sample the first core tensors, and then fix the other core tensors. In this case, we can further improve the speed of algorithm. But still, it costs a lot of time, and we are wondering if this is a very new research. So because a large language model is very powerful, so we try to ask if large language model can also develop new algorithm based on our past algorithm. So the first step is large language model if they can understand our algorithm, and also if they can it can do some reasoning and to inference to new algorithm. And we try to do this to first input large language model with our Python code. Like we give them several algorithms. We try to ask a large language model to try to, like a programmer, to do some combination. Maybe it's the combination with different algorithm A and B, and then we generate a new algorithm. And finally, we found they generate a lot of code. Maybe some of them don't work, and some algorithm it works. And we choose some algorithm which works very well. And here is some results. We show that actually they can generate maybe sometimes the good algorithm based on combination of past algorithms. But this is very preliminary results. Okay, so finally, we also wonder when we use tensor network to represent the neural network parameters, how is the robustness of a neural network affected? So we analyze theoretically very like basic neural network. One is fully connected layer, another one is tensor layer. So we show that actually when under the standard training, there is no any difference, but in adversarial training, so which is a trained model to prevent adversary attack. In this case, the robustness, the error bound are changed. It's depend on the number of parameters and depend on low rankness. So that means when we do the adversarial training of a neural network, so low rankness and the tensor network representation of parameters can be helpful, and with a small error bound. And in this case, because when we have a well-trained neural network, actually they don't satisfy the exactly low rank structure. So we also show that even it's approximately low rankness, It's also we can get a very better error bound when we use low rank approximation for the parameters. And in the last part, we also try to improve the adversarial robustness by developing adversarial purification method. That means we try to pre-process the data before feeding into the classifier. We try to remove the perturbations, but such kind of perturbation is very difficult to remove as Gaussian noise. So now the state art is using very powerful like generative model, diffusion model to remove. But the diffusion model are difficult to, diffusion model are usually pre-trained and they cannot well designed for this task. So our idea is to make diffusion model is well adapted to this task. So we use some kind of new loss function and to do the fine tuning for the generative model. To finally, we have a adversarial training on purification. And we can see that actually we can achieve same robustness as adversarial training method, but the good point of adversarial purification is very good generalization to the unseen attack. But in general, adversarial training is only robust on the seen attack, but not well generalized to unseen attack. So this is the adversarial purification, the benefit of adversarial purification. So in fact, in summary, I think tensor network may be a powerful tool to represent high dimensional structured data and can be applied to deep learning to improve robustness or interpretability or some kind of efficiency. Okay, thank you very much.
Thank you very much. Any questions or comments? In a collaboration with the LLM, what kind of problem has been solved?
What kind of problem we solved? We try to solve the tensor network structure search. Okay, this is our basic problem given given a tensor. So how to choose optimal tensor network structure? So that means how to choose the best adjacency matrix using the given a tensor. So, and previously we have some algorithm like random sampling, also some kind of this algorithm. And in LLM, so we input several algorithms in Python code as an input to large language model. And we try to ask large language model if they can do some research or they can propose some kind of new code which generate the similar result. Just like us to develop a new algorithm. And the input is Python code, output is also Python code.
So researchers are not important.
We try to mimic the researcher. So this is the researcher, so like overview paper and the set. No, this can help us. Yeah, maybe we can use. Yeah. Yeah, but many code are not good. We need to choose manually. Some code generated has better result. Because they can guarantee the grammarly correct. Yeah, but not always works well for the problem.
Okay, interesting.
Any questions?
Have you used or do you know if this tensor structure can be used for anomaly detection tasks?
Yeah, maybe, but I'm not sure. We can use, when we consider the data tensor, we can use low rank approximation and outlier capture to find some, if there are some kind of outlier inside the data. If this outlier is considered as anomaly detection. Yeah.
Okay, thanks. Okay, let's thank the speaker again.
Thank you.
Thank you for the introduction. I'm Kazusato Oko from University of Tokyo and RIKEN. Today I'm going to talk about learning theory to learn many different features in high dimension. So this is kind of theory work. So this is a joint work with my wonderful collaborators using Son, Taiji Suzuki, and Day2. So let's start. So first, I would like to introduce a class of problems we consider today. So this is a formal definition. So which is called rich combination. So I think this is really feel like a theory at first glance, but the definition is not too complicated. So let me explain. So first, the input X is sample from high-dimensional standard Gaussian. Right? This is quite important. So and the definition is, the dimension is referred to D. So we say this is D-dimensional problem, and we're interested in how to learn features in high dimension, because the real-world data is often high-dimensional. And next, we define Y. So Y consists of noise and a function term, and a function consists of some, has some additive structure, right? So, each function only depends on one direction V, and such function is also called rich function. This is why we call this as rich combination. Okay, so we learn a summation of functions that only depends on one direction at the same time. So also, we consider a situation. Well, we consider a situation where the feature vector Vm points diverse directions, meaning that they are nearly orthogonal to each other, rather than concentrating in a few directions. Right? So this is mainly because when you randomly sample two vectors or few vectors in high-dimensional space, then they are almost orthogonal. This is a later. Okay. And we're interested in a specific regime when the dimension D diverges, as well as the number of components, features, M also diverges. Thus, we are interested in a regime where the features to be learned and the ambient dimension both diverges. This is based on the natural guess that when the dimension diverges, when the data becomes high dimensional, then the data is expected to have more information. So that's why. Okay. And well, so this is a problem we consider today, but I think many of you are not convinced why we consider this problem as a learning theory, not as a mathematics. So I'll explain three different motivations from now. So let me explain them. So the first motivation is additive model. Right? The whole function that takes high-dimensional input is quite complicated, as you know. So we cannot learn all of them in a realistic time. Like this figure, this is only two-dimensional figure, but this is complicated, right? So this cannot be learned. Okay. So a natural solution to this is to, assume some structures on the model. For example, and one such structure is the true function f, can be written as the sum of simple function. So this is the basic motivation of the additive model. And by using this restricted model, it gives a better generalization ability because the model is simpler, and you will also have interpretability because you can interpret what kind of features along, what kind of structures along as a result of optimization. So this gives the interpretability. So and one of the representative example of the simpler function class is rich combination, of course, because obviously assuming the additive structure of univariate function is very simple, right? So indeed, there's a long history of rich combination mainly in statistics, and many methods have been proposed. But the problem is that many literature mainly focus on statistical guarantees, not optimization, and they assume possibility of non-convex optimization as a black box. Right? So polynomial time optimization guarantee has not been obtained for large class of problems. especially when you do not know which direction VM should be taken. So if VM is prefixed, then you can maybe do some regression, but you can, if you need to search VM, then you do not have polynomial time counting. So given the importance of additive model, or in the statistics literature, we need optimization guarantee on this. So this is the first motivation. Right. And the second motivation is recent feature learning theory, representation learning theory of neural network. So it has been shown that neural network can learn low-dimensional features, low-dimensional data, the high-dimensional data efficiently when the data has low-dimensional structure. So meaning that the input, whole input X is three-dimensional, which is very high-dimensional. But if Y only depends on a few coordinates, V1 to Vm, and M is constant, then neural network can efficiently learn that kind of functions. So in other words, sparse means the target function depends on only a few directions. Okay? So contrary to neural network, traditional methods like counter method or the random feature, they cannot learn such function very efficiently in high dimension because they fail to learn a higher degree component. So this is an intuitive interpretation of what's happening in high dimension. So the realistic data cannot be, if you do a Taylor expansion, then that should not be purely quadratic or degree 3 function or so. So they always have higher degree component. And if the data has a kind of low dimensional structure like this, then the neural network can essentially learn the function like this. But if you apply a traditional method like random feature or counter method, then the prediction of that model is more like a low dimensional approximation of that function. Like this looks like a very linear approximation, right? So yeah, based on this kind of analysis, we can say that neural network is superior to traditional method for a specific type of problems, which have sparsity on the number of relevant coordinate features. But the natural question would be, how many features can be learned simultaneously by neural network? But the existing theory is limited to the case when a constant number of features are treated. So this gives another motivation to study rich combination. Okay. And the third motivation is the paradigm of large-scale pre-training. So as you know, foundation models are trained with a huge size of data, right? So which is a collection of different data sources. So for example, the pile dataset, which is quite common in training of large language models, has 800 gigabytes, consists of many different data sets like Wikipedia or archive or and so on. As a result, the pre-trained model exhibits an interesting property. So features for different tasks are localized in a small part of parameters, small number of parameters in a whole model. So empirically, this is observed. There's many evidence. For example, if you specify the language model, then 95% of the performance of the original model can be maintained with only 0.1% of the parameters. Right? You can specify the rand model for specific task. Or maybe, which is more familiar to you is low-rank fine-tuning, LoRa. So, where fine-tuning requires an update of only a few number of parameters, where you try to, extract a few relevant features like, style of some specific painters, right? Yeah. So therefore, the pre-trained methods, pre-trained models have localized features, which is considered the key to the adaptivity of large language models or foundation models. But we do not know a theory to deal with many feature directions simultaneously. So as a result, this gives us a strong motivation to start a rich combination in a regime when the number of features diverges as the dimension grows. Okay. So to summarize, for the additive models, because polynomial time optimization guarantee does not exist, so we consider optimization of rich combination. And for recent representation learning theory of neural network, interesting results of learning sparse functions have been obtained. But we want to know how many number of features can be learned simultaneously, right? And for large-scale pre-training, localization of the feature must be the key, but we want to reproduce it in a legal theory. So this is why we studied rich combination. But in this talk, we mainly consider two things. So one is that neural network can actually efficiently learn rich combination via Gaussian-based training. And the second is how to measure the difficulty of this problem. Okay. So let's proceed to the analysis of neural network. So in this talk, rather than going to the details of analysis, I want to explain what we prove and why we need to prove it in high level. So for this, I would like to begin with the limitation of the traditional methods like kernel or random features, okay? And we each use a fixed feature map. So specifically, when the number of data n is about d is the dimension, so d to the q, right? So n is d to q, and the appropriate assumption, then the generalization error of the kernel or random feature method in the left, right? So this is the generalization error of kernel or random feature method converges to some specific value, and this is the best approximation of the target function with degree q polynomials. So as I said, traditional method cannot run the higher degree term, higher degree component efficiently. And in more rigorous sense, that if you have n to the d to the q sample, then you only learn degree q part of the target function. So this is a strong result in kernel method study. So this clearly describes, unless n is very large, the solution of this method is no better than low degree approximation. Right. Oh, sorry. No. Well, I didn't say this right. Okay. So the reason behind this is intuitively explained. The random feature model is a special, so let's take random feature as an example. So random feature model is a special type of two-layer neural network. So where the first layer weight is sampled from d-dimensional Gaussian, so this is rotationally invariant, and we fix the first layer. We do not train the first layer, and we only fit the second layer to the data, right? So this is the random feature model. But in high dimension, a randomly sampled weight vector is nearly orthogonal to the feature vector, right? Because this is high dimensional. So therefore, even if we train the second layer, we cannot find a good solution of the second layer to efficiently approximate the target function, because when the target function is row dimensional. So this is the main reason why the fixed feature map is not adaptive to approximate a higher degree term. So now you know that learning feature direction is important in high dimensional learning. In the recent neural network theory, a seminal work of Damin et al. Discuss how to learn sparse polynomials, polynomials that only depend on few directions. How to learn them efficiently. So in their analysis, they only train the first layer for only one step. But this is a simplification for the theory, but this one step has a significant meaning, significant improvement over the kernel method. Why? So this is because the updated first layer is dominated by the left term, right? So where the Hessian, this is the Hessian times the initial value of the weight vector. So the Hessian only maps W, the initialized first layer weight, onto the subspace spanned by the feature directions. So if the feature direction is from E1 to EM, then this Hessian is expected to span the E1 to EM, and then the mapped first layer weight will span only the relevant subspace, right? So because otherwise the Hessian value is 0 in other directions. Okay, so thus the updated weights distribute in the span of the feature vectors, like if the important relevant dimension is E1 to EM, then the span is the first layer weights distribute over the span of these vectors. Okay. So then they train the second layer as the same as random feature model, and as a result, their model is like a random feature but weight vectors are initialized only within the relevant subspace. So random feature succeeds to approximate higher degree component as long as m is a constant, right? So this is why neural network can learn sparse functions very efficiently according to their theory. Okay. Well, however, we are considering the regime when m goes to infinity as d diverges. So, but the previous theory says that the trained neural network is a random feature model with weights restricted to a span of relevant dimensions. So thus, when m is large, the same problem happens. The neural network will require m to the q sample, as the same as random feature model, because the trained neural network is only a random feature within the relevant subspace, right? So when the number of feature direction m close with d. So as illustrated here in the left side, each component does not have enough number of neurons to approximate itself when m is large, m becomes large. So, well, as a usual, random feature model fails, right? Thus, what should be the distribution of neural network first layer neurons? So probably the weight distribution should be like this on the right side. So, some neurons should localize into a specific direction rather than distributing over the span of the relevant subspace, right? So this will be the right figure. So this is why we need to show the localization of neurons, the first layer weight, to the direction of only a few directions rather than span. And proving reliability of rich combination for that, proving this kind of weight distribution is crucial. So we want to show the localization of the first layer weight. Okay. So before presenting the theory, we first show the experimental result. And this clearly shows that we trained the neural network with in a feature learning regime and neural tangent kernel regime. And in the left, the feature vectors is E1 and E2. So this is aligned with the coordinate direction. So if you look at the left figure, then the first layer weight is actually aligned with the feature direction, right? But if you look at the right, the kernel regime, the neuron does not move from initialization and no alignment is observed. So this is a clear difference between feature learning regime and the localization regime and the kind of kernel regime. Okay, so we want to show this happen in a rigorous theory. Okay, so from now we go to a bit of formal theorem. So to briefly set several assumptions, first we assume that the link function is degree q polynomial, and here q can be large, say 100 or so, right? We consider its Hermite expansion after that, and this is basis expansion of the link function. And we assume we assume some condition on coefficient, or specifically the first two coefficient to be 0, and piece coefficient to be non-zero. But this can be satisfied if you do a kind of pre-process, and if the function is not adversarial, then you can satisfy this condition with p equals 3. And the second assumption is the feature vectors. So they are assumed to have known 1 and to be nearly orthogonal to each other. And the number of classes, number of problems, Fm to be run at the same time is bounded by the inverse of inner product of them. But in high dimension, the vectors are nearly orthogonal. So if you randomly sample the vectors, then M can grow with D. So, and the model is 2-layer neural network with rel activation, and the loss is a square loss. Both are quite standard. And the only modification for the theory is a layer-wise training. So we first train the first layer and then train the second layer. This is for simplicity. Okay. And very, very briefly, I'm going to explain the overview of the proof to show localization. Okay. So in the proof, we track the value of the alignment. So the alignment is, not the alignment in large language model world, So the alignment is defined, simply defined, as an inner product between the feature vector and the weight for each direction. Right. So after a lot of approximations, we obtained that the alignment evolves according to this differential equation. Then it's going to be like this. Right. And this, the value, this equation is one, that suddenly blows up at a certain time point. Right. So which is very sensitive to the initial value, initial alignment. And because the blow up happens in a very short time, at the same, at the time one direction blows up, the other direction remains small. Right? And after that, the alignment for only one direction continue to go, but the other direction does not evolve anymore. So, well, the neuron finally localized into one specific direction. So this is a very high-level overview of the proof. So let me present some SLM. So by taking the parameter appropriately, we can show that the trained neural network achieves epsilon generalization error in error loss. And what matters in terms of statistical theory, because we've already proved the optimization side. So what we need to care from now is a statistical guarantee. So in statistical theory, so the sample complexity we require is m times d to the p minus 1. But as I said, p is only for assumption, and usually p can be taken as 3. So m to the d to the 2, m times d to the 2 is the usual complexity for this problem. And now there's one previous work that considers the case of m equal 1, and if it says m equal 1 in our analysis, then this matches. Right? And what is more important is the comparison with traditional method. Right? For the kernel or random feature method, you need d to the q sample. Q is the maximum degree of the target function. And if you, we didn't prove this rigorously, but intuitively, if you use subspace random feature like analysis, then the required complexity will be m to the q. But as I said, q can be as large as arbitrary large as 100, 200 or so. So when m grows with d, then our analysis is much tighter, and the key is the localization of neurons. Okay. Well, so finally, I want to present some hardness, computational hardness result when we arbitrarily take p, the minimum degree of emit expansion which has non-zero coefficient. Okay. So we want to quantify the difficulty of learning rich combination. But how should we do? So one such approach is a statistical query framework. So let me explain. So in this framework, there's learner and oracle, and learner aims to output a function that is close to the target function. Right? And in order for that, the learner asks what the target function is by giving a query and a tolerance. A query is a function that takes x and y, and a tolerance is a kind of accuracy. And then the oracle returns any value, can return any value, any one value within tau, at most tau apart from the expectation of gxy. G is a query, right? But here the noise can be, adversarial. So you can guess that if tau is too large, then the oracle can hide the all information about the function, true function, and the learner fails to learn a true function. Right? So we have some upper bound on tau to learn the target function. But because tau is a scale of the noise, and the sample size is also define the scale of the noise, right? If you take a high probability bound, then how many number of sample you have determines how large the noise is. So there's some connection between this tau and the sample size, and by using this kind of connection, we can interpret the upper bound on tau into a sample complexity lower bound. So, well, we obtain the following lower bound on the sample complexity. So in order to learn a randomly sample rich combination with p sufficiently large, then you need this sample complexity. But here in the exponent of d, there's rho. But if you take p to infinity, then this rho also go to infinity. So meaning that if you take larger p, then you can make this problem arbitrarily difficult. Okay. So this theorem says that problem can be arbitrarily difficult in that it requires more sample as p increases. But this rho bound itself is not only the interesting result. So this bound is for the algorithm with polynomial time guarantee. However, if you use exponential compute, then only n times this sample suffices for any p. So therefore, here is clearly a gap between sample complexity required for polynomial time optimization and the statistical complexity with infinite computation. So this is sometimes called statistical computational trade-off, meaning that you cannot achieve the shortest training time and the best sample size. They are incompatible. Okay? So let me conclude the presentation. We consider the problem of rich combination. And this problem is, input is high-dimensional Gaussian. Y consists of the summation of single index models. And the features points out the diverse selections. And this is motivated by three different reasons. And as a main result, we show that network can efficiently learn rich combination with gradual training. And the core of the analysis is localization of the neurons. On the other hand, we also prove the difficulty of this problem by giving a statistical query lower bound. And we found that the interesting computational statistical trade-off. So this is the end of the talk. Thank you very much.
Maybe it's a good time. Okay, let's thank the speaker again.
Thank you.
Thank you, and hello everyone. I'm Thomas. I'm a research scientist here at RIKEN AIP, working with MTS Khan. And I'm presenting today our recent work on variational inference, or we call it variational learning, applied to very large neural networks. So the background of this work, I mean, I don't have to say much about it, but as you are all aware, people are training very large neural networks on very large data sets, and amazing things have happened. And this kind of success has led to the belief that, well, among some people in the community, it has led to a belief that maybe scale is all you need and AGI is coming. So if you go to the large conferences, you encounter maybe someone with a t-shirt like this, and one of them told me, "Oh, your research is useless. We already have everything. You just need to scale up your models. You just need to scale up your data set. What are you doing with your complicated things and so on? We don't need it." And of course, I don't believe in this, but maybe there's a lesson to be learned. And one famous researcher actually called this the bitter lesson, that the simple ideas that scale up and the simple methods, they will be the ones that prevail. And maybe the more complicated methods that don't scale, yeah, it's unclear whether they will be successful. So this is somehow the mindset of this work, that we try to construct a variational inference or a variational learning method that is very simple, has no overhead at all, and scales to very large neural networks. And we show that by doing this, actually, we can have a Bayesian inference method that works very well. So we have seen these amazing successes in deep learning, and of course, there's some difficulties that I believe cannot be solved with scale. And so these two problems will be adaptation of large neural networks and understanding of large networks. And I hope to convince you today that these variational learning approaches, they can address these two problems. So as we know, it's difficult once we've trained our neural network, it can sometimes be difficult to adapt it. So OpenAI trained on this New York Times data and has been difficult for them to remove it from the model. And these people are getting very interested in machine unlearning, which is the ideas to kind of remove data from the model, so to adapt it, to remove the knowledge. And also it's important to know whether updates to the model can hurt its capability or improve it. So of course we need to update our models continuously as the world is changing, and if we do this in not such a careful way, maybe our model will get more stupid. And sometimes people cannot adapt their model and they just stop deploying the model because they just cannot change it that quickly. On the other hand, these models are often very certain and wrong and make up a lot of things and so on. And there's sometimes the results are quite hard to understand. And we have these adversarial examples that we've seen in Qibin's talk. So yeah, there's a lot of issues in general in deep learning about model adaptation and model understanding. And then the question is, can we solve this simply by scaling things up? And I believe not. And we need some new fundamental ideas. And today I want to convince you that a kind of Bayesian approach that is still very scalable can address these two problems. So let me take one step back to a very clear setup. So this is the typical optimization problem that people consider in deep learning, empirical risk minimization. We minimize the loss plus a regularizer, and then we train our model on some data and we get the solution. Then the question is this a good solution or not? And maybe I train again. And since it's heavily over-parameterized and I have very little data, I get maybe another solution. And then which one is better? And I can do this many times and I get a bunch of solutions basically. And what I'm advocating for is that we should not find a single solution theta, but rather we should search for a probability distribution, which I call Q of theta in this talk, which sits at somewhere in some low region in the loss landscape, and it collects these multiple hypotheses. And the intuition, so I talked about adaptation of neural networks and understanding of neural networks, and having this distribution available, it basically tells you about your solutions in the neighborhood. So you also know what happens if your model changes, you can understand how the solution changes. So having this Q of theta available will be very useful for understanding these models and also adapting them. Because you can see in these regions where there is no data, these curves, they spread out. And this basically means when new data comes in, you keep your mind open for multiple solutions, and then you can adapt much quicker to the new data. Rather than if you would have focused on a single solution, it would be very hard if that single solution would be very conflicting with the new data that comes in. So what is the correct framework to learn such a distribution Q of theta? We can simply modify our optimization problem, where we don't search for theta, the parameter of the neural network anymore, but we search for distributions Q of theta. And we do this by having this expected loss term and the entropy term. And so the point is to search for this Q of theta such that we can sample from that distribution and we get solutions, theta 1, theta 2, and so on. And this expected loss term basically tells us that models drawn from that distribution should have low loss. And the entropy term tells us that the models drawn from Q of theta should be diverse. So we are searching for a diverse set of models which all explain the data well. This is the idea of this modified optimization problem. And yeah, throughout this talk, I will always in red annotate the things we add on top of the standard deep learning toolbox. And yeah, as I explained before, having this Q of theta is very valuable for model understanding and model adaptation, which I also will show at the end of this talk. So why do we call this Bayesian? So actually there's a connection to Bayesian inference of this loss function. You can split up the expectation by linearity and then notice that this term is just the Kullback-Leibler divergence to some distribution P of theta, which we call prior. And then if we solve that, it's a strictly convex optimization problem in the space of all distributions. If we solve that, we have a closed form solution, e to the minus L of theta times P of theta. And if L of theta is a negative log likelihood of some data set, then the solution in the space of all probability measures is just the Bayesian posterior. And this has been noted long ago in this 1988 paper. So this kind of intuitive modification of our optimization problem led us to Bayes' rule. And what we do in practice, of course, it's difficult to optimize in infinite dimensions. So what we do in this talk here to get a very scalable method, we restrict Q of theta to a family of distribution, which will here be Gaussian distributions with a diagonal covariance. So of course, this idea of variational inference for neural networks is a very old idea. One of the first papers is by Geoffrey Hinton, keeping neural networks simple by minimizing the description length of the weights. So this was motivated not from this adaptation or understanding viewpoint, but rather from a regularization viewpoint. So there are many benefits of this Q of theta formulation. And in this paper, it was motivated that by minimizing this entropy or solving this maximum entropy problem, we are actually compressing the data. So it gives a very strong regularization, which can maybe improve the generalization of the neural network. Then in 2011, Alex Graves, he was a postdoc with Geoffrey Hinton. He proposed this practical variational inference for neural networks paper, where he already showed that this actually works quite well for LSTM in speech recognition. But the work was kind of forgotten. And in 2015, another paper was proposed by Google researchers on weight uncertainty in neural networks. And also from our group in 2019, these variational learning methods were scaled up to ImageNet scale. But despite these advances, the community somehow doesn't believe in this variational learning. So often people say it doesn't work or it's difficult to tune and so on. So the goal of our work was to show that this can actually be made very, very practical. At the same time, recently a paper appeared, not so recent anymore, but in 2020 called Sharpness-Aware Minimization for Efficiently Improving Generalization. It sounds like a very different topic, but this has been a very influential method now, which is already used in practice, cited over 1,000 times, and for example, used by OpenAI to train the CLIP model. And what we've shown in our work actually last year was that this Sharpness-Aware Minimization method, it can actually also be seen as a method which solves this Q of theta objective for a fixed Gaussian prior and isotropic Gaussian posterior. So we already have a variational learning method here, Sharpness-Aware Minimization, with very simple Q of theta, which is very successful in deep learning. And what we've shown in our work here in 2023 is that this method actually minimizes an optimal upper bound to this Bayesian objective, which is obtained using a tool called the Fenchel biconjugate. Then, of course, if this method is optimizing an upper bound, it seems much more direct to not minimize the upper bound, but to optimize the objective directly, which leads to these direct optimization methods. And they also have been considered in the community, not from the viewpoint of variational learning, but they call it noise injection for improved generalization. But essentially, it's a minimization of this objective for an isotropic Gaussian posterior. And there are several such papers. And these noise injections have also been studied long ago. So this is, in some sense, it's also known that injecting noise during training can improve the generalization. But somehow there's a disconnect that the variational inference is considered impractical, but at the same time, people use Sharpness-Aware minimization or these noise injection approaches. And with our work, we hope to fill this gap, that we propose a variational learning method that can work well on large neural networks. The code is available. And basically, the main idea is that you estimate a Gaussian distribution for every parameter in your neural network, which is your Q of theta that I've showed before. And we ran this, for example, on GPT-2 for different sizes of parameters. So this is I1. The method is called I1, Improved Variational Euler-Newton Method in red. And we have a very well-tuned MW baseline. And we ran it for 125 million, 255 million, and 773 million parameters. And as we increase the scale, we can see that I1 is not only competitive with AdamW, but seems to gain an edge as the model gets larger and larger. Yeah, the method also works on ImageNet. So this is a ResNet 50 on ImageNet, where we can also match the accuracy of AdamW baseline. But maybe more interestingly, on the right-hand side, this is a calibration diagram. So our optimal method will be on the diagonal. We can see AdamW in gray. It's slightly overconfident. So it's very confident when its predictions are wrong, whereas this I1 method is actually slightly underconfident, but much better calibrated in general. So what is this method doing? So essentially it's doing gradient descent on the objective function that I motivated at the beginning of the talk. So we parameterize our Q of theta as an exponential family with parameter lambda. So lambda contains both the mean and the covariance of our Gaussian distribution. And then we do natural gradient descent in this lambda coordinate system. So F inverse is the Fisher information matrix. And the lambda update from the previous slide, we can slightly rewrite it in M and H. There's no approximation or only a stochastic approximation, but this is a rewriting of this gradient descent equation from the previous slide. And what we get is an optimizer that is very similar to RMS prop or Adam with some key differences. So in the first line, we see RMS prop just evaluates the stochastic gradient at theta, whereas we evaluate the stochastic gradient at a perturbed point. So we sample some random noise, and this connects to these noise injection methods and also sharpens aware minimization, where we kind of perturb our gradient evaluation. Then for this preconditional computation in Adam, we use squared gradients. Here we have a slightly different computation. And this computation in expectation, it computes the Hessian of the loss. So this is an unbiased estimator of smoothing of the Hessian matrices. That's why we call it Newton method. And it's quite computationally cheap. Typically, these second order methods for deep learning are expensive, but here we can simply use the gradient also to estimate the Hessian. Line 3 is exactly the same as in Adam, and line 4 is also the same, with the difference that we don't precondition with the square root, but with H itself. And then from these M and H variables, we can compute our posterior distribution Q of theta, which will be a solution to this optimization problem over distributions. And the covariance sigma square is related to H, and the prior delta times a temperature parameter tau, which is in front of the entropy. Actually, I omitted it before, but it can control the spread of our Gaussian distribution. So as you can see, this method has only very slight overhead when compared to Adam, which is essentially this sampling of random numbers, and that's why it can scale to large problems. It's available, so you can easily plug it into your PyTorch code. You simply replace your optimizer with I1. You have to include this additional for loop over your training samples to do the. So this is the random sampling. So train samples is, for example, set to 1 in the pseudocode before, but you can also use more random samples. So it's easy to integrate into your training code, and yeah, it can work well on the standard benchmarks on ImageNet and CIFAR 10, CIFAR 100. There's more results in the paper, but we can not only improve the generalization, but also these calibration metrics like expected calibration error. So the method is actually quite related to second order optimization methods. So we call it variational Newton method. And recently there have been trending methods for second order optimization for large language model pre-training. So one method from Stanford University is called SOFIA, a scalable stochastic second order optimizer. Another method from Berkeley called other Hessian. If you look at the pseudocode, they look related to I1, but they have to use this Hutchinson estimator to compute the diagonal of the Hessian. And for this Hutchinson estimator, they have to artificially inject some noise and use Hessian vector products, which induce additional overhead. And our variational formulation, as you've seen, can directly estimate the Hessian using only the gradient. So it's more efficient. But nevertheless, this SOFIA method has been hyped a lot on Twitter by the authors. So they say you can save $1 million if you use that optimizer because it's 2 times faster than Adam. And actually, people have independently reproduced these results at Facebook. They are now training 70 billion parameter models with SOFIA. So these methods are not only hyped, but they seem promising. But we believe that our I1 method that we propose has some advantages actually over this SOFIA optimizer. Yeah, we also compared to other Hessian, where on this data set we could get better results. But maybe let me conclude the talk now with some applications of having this distribution Q of theta available. Here in this experiment, we trained on CIFAR 10, and then we plug in street view house number data into our model. And we look at the predictive entropy of the model. And ideally, we want on the in-domain data it was trained on, we want this distribution, this entropy to be quite peaked. We want the model to be certain. And on the out-of-domain data, we want the model to be more smoothed out. And SGD does an okay job, but you can see that here we still have on this out-of-domain data quite low entropy. So it assigns very high confidence to some street view house number digits that they are bird or car or something. So a good method will really separate these 2 distributions. And existing Bayesian methods, they manage to do this. So the space by backprop, this ICML 2015 paper, MC Dropout, and SWARC. But they do this by just smoothing everything. You can see that the red distribution also gets more smoothed out. Whereas this I1 method, it manages to keep the high entropy for the in-domain data while smoothing the out-of-domain data. So this can be used to detect out-of-distribution data. And actually, we used a very early version of this work already 2 years ago. So this was an earlier version of I1, but we used it to win the NeurIPS 2021 challenge on approximate inference in deep learning. So it's among the most accurate approximate Bayesian inference methods in the world. So these 2nd and 3rd place, there were also combinations of stochastic gradient Langevin dynamics and SWARC and so on. So let me get back to the 2 problems in deep learning that we have, namely adaptation and understanding. At ICLR this year, we had a paper on model merging. And so the idea of model merging is that if you train on separate models on different data sets, you can combine them by averaging their parameters. So this has been a popular method to kind of adapt neural networks by averaging in models trained on new data, or also removing the toxic data by training a model on toxic data and then subtracting the parameters. And in this distributional framework, this can simply be viewed as a multiplication of distributions. So if we want to combine knowledge, which is represented by a Bayesian posterior, we simply multiply these posterior distributions to get our combined posterior. And then in the approximate Gaussian case that we consider, this simply leads to a weighted averaging of the parameters, which improves, or which we show in this paper to improve over the task arithmetic, which is simply a averaging of the parameters. And this 2nd order information here, this uncertainty Hessian matrix, it's approximated by I1. So if you train your models with I1, you can adapt them much more quickly because you have this neighborhood information available in the covariance of your Gaussian distribution. And yeah, we evaluated this on some data sets, but maybe I skipped this. Then about model understanding. This was a paper we had at NeurIPS last year where we used the covariance estimated by I1 also to understand the model better. And there we derived a very simple equation that the sensitivity of a data example is proportional to the prediction error times the prediction variance. And this is related to influence functions, but generalized to this distributional viewpoint. And again, this prediction variance can be computed by I1 for free. So by training with this Q of theta distribution, we can approximate influence functions in a very efficient way. So running this on ImageNet, here's just some examples. More details, I refer to this NeurIPS paper here, but we can estimate for each data example in the data set how sensitive the model is to that data point. You can see that the low sensitivity data points are all quite mundane. The high sensitivity ones contain interesting edge cases, like a llama with a jetpack or a shark stuck in the top of a roof. So it's actually quite enlightening to see what kind of strange things there are in the ImageNet dataset. Okay, so let me conclude the talk. So in contrast to common beliefs that variational learning doesn't work, we actually show that it can be very effective for large deep networks, such as GPT-2. And the proposed method is actually among the most accurate approximate Bayesian inference methods in the world. We've won this NeurIPS competition with the method. And we strongly believe that variational learning can help to solve two very important problems in modern deep learning, which is the model adaptation and model understanding. And the code is available. You can just run pip install I1 and yeah, please try it out. So thank you very much.
So any questions or comments? Maybe a technical one is in the assumptions of the introduced in the beginning of I1, you assumed that the exponential family.
Yes.
How did you design the statistics T? T theta, T of theta.
So here we just pick a Gaussian distribution. So T of theta is just theta, theta squared.
Oh yeah.
Yeah.
I see.
But you can consider different exponential families, and they will give you different optimization algorithms. So this is actually a general framework to design many algorithms. But just for this theta, theta squared, in T of theta, you recover some Adam-like optimizer. But if you would include like higher order moments, like theta cubed or theta to the power of 4, maybe you would get a more
different
higher order method.
I see. So, but in practice, T theta equals scale theta works for deep network?
Yes.
Oh yeah.
There's no overhead because in Adam you also have two variables.
Yeah.
So the running average of squared gradients and the mean, and these correspond to the theta squared and the theta. So that's why it has exactly the same cost, and it can work well for very large neural networks.
Okay, that's interesting.
So, but I thought you learned the distribution of data.
Yes.
I'm wondering when you do the inference, do you also consider the distribution of data, or you just how efficient?
Yeah, you can do both. So this in this table, I1 at mean is just the prediction at the mean of the distribution. And if you do sampling here, I think it was 64 samples, the results improve. So if you really use the distribution, you can improve also the generalization, but you will have an overhead in inference. It will be much more expensive. You need to do many forward passes. But there are also ways to make this cheaper again, maybe using some distillation approach or something.
Thank you for the great presentation. I'm here.
Oh.
So I was very interested about the uncertainty estimation you had at the end because it's very useful measure on how your testing is going to work. And I was very curious if you have a part of this plot which is qualitative. If you have any way to assess that the uncertainty you estimate is actually correct. Is there any empirical way to do that, or do you have any idea on how to do this?
Yes, great question. So we believe there's many downstream applications, actually these model merging. If your uncertainty estimate is good, your model merging will improve. And also for model understanding, it's kind of better uncertainty estimates lead to better sensitivity estimates. And it's not only about these two applications, but there's applications, for example, in continual learning, where you update your distribution continuously. And good uncertainty will also be useful for that. So I think the main way to benchmark these uncertainty estimates is really to look at some downstream applications, like continual learning or model merging, model understanding, and seeing that they really get significantly improved.
Yeah, it could be also a good strategy to, for instance, to fetch samples, but
Yes.
somehow retraining reduce the uncertainty of your model, and so you could do a bit more of labeling on something that, for some reasons, your model is being more uncertain about, or to have some reinforcement learning or strategies to improve automatically the models as well. I think it's very powerful.
Yes, so exploration and reinforcement learning, active learning, all of these, if your uncertainty is good, they should be improved. Mm-hmm. So I think these are good ways to measure the uncertainty quality.
Great, thank you.
Thank you very much. Any other questions?
The question is, how does I1 address the issue of scalability in variation learning for large models? And are there any specific domains or applications where I1's approach is particularly beneficial? So the issue of scalability is mostly addressed in this diagonal Gaussian posterior formulation. So we make it very similar to the existing deep learning methods. And by construction, it's scalable because there's no additional overhead. Regarding the second question, what kind of applications it's particularly suited to, I would say, I mean, the main points I made is this adaptation and understanding applications. But in all situations where you need some kind of uncertainty estimates, I would recommend using this.
Okay, then time is coming, so let's thank the speaker again. And